figure out the probability that you buy an 8-pack and there's no winner in there. Well, on the AP exam, we're on a test. Excuse me. You may be asked to make a simulation and carry it out. And so using dice for a simulation wouldn't always be plausible. So we have to know how to use our table of random digits to design the simulation and carry it out. Excuse me. Grab the wrong orange one. So we're going to do the Mountain Dew simulation, but we're going to use the table of random digits. This time, not a die. So still the 4-step process, but I didn't put state down here because there's no point in me restating the exact same question down here. The things that are going to change are the plan, doing it, and then my conclusion. So, just as a reminder, Mountain Dew claims that 1 in 6 bottles would have a prize or is a winner. So we need to use our table of random digits to have 6 numbers, 1 that represents winning and 5 that represent losing. So just to stick with what we did yesterday, I'm going to say 3 means we won. 1, 2, 4, 5, and 6 mean we lose. 3 means we win. 1, 2, 4, 5, 6 mean lose. Now on the table of random digits, there's 7, 8, 9, and 0. So I have to specify what those 4 numbers mean as well, or what I do with them. In this case, 7, 8, 9, and 0, I'm going to ignore. So if I get a 3, I won a prize. If I get 1, 2, 4, 5, or 6, no prize. 7, 8, 9, 0, I ignore. Just like before, 1 repetition is going to be 8 numbers. I can have repeats, just like I had repeats up here. So I had 4 twice, 6 twice. They're not people. The numbers don't represent people in this situation, so I can have repeat numbers. So 1 repetition is going to be 8 numbers between 1 and 6. Excuse me. I'm going to abbreviate between. And then just like before in the do, we're going to want more than 1 repetition. I'm going to go with 5. A lot of times, if you're asked to carry out your simulation, it'll tell you how many repetitions to do. We're going to do 5 here just so we have more than 1. Obviously, like I said yesterday, the more repetitions of your simulation you can do, the better, but it's not always feasible. And somebody give me a number 1 through 50.
26. 44. 26.
I heard Eric
31.
first, and he said 3. So I'm going to start at line 103 on my table of random digits. And we're reading single digit numbers. So hopefully this should go pretty quick. Let's see. Find something that I can kind of use to. So 103, we have 4, 5, 4, 6. Then we get a 7, which we're going to ignore. Then we have 7, 1, 7, 0, 9. We ignore all those. 7, 7. And then we have 2 5s. And that's 1, 2, 3, 4, 5, 7. 8 we ignore, 0, 0, 0, 9 we ignore, and then we get a 5. So there's my first repetition. And then I keep going where I left off to start my next repetition. So I have 3, 2. Then I have an 8, which I ignore. 6, 3, 2. Then I have 9, which I'm going to ignore. 4, 8, 5. That's 7 numbers. Then I have 8, 2. So there's my next repetition. Then I have 2, 2, 6. 9, I ignore. 0, 0, I ignore. Then I have 5, 6. And that's the end of line 103, so then I'm going to go down to 104. Then I have 5, 2, 7 I ignore, and then I have a 1. And that's repetition 3. Picking up where I left off, I have 1, 3, then I have 8, 8, 8, 9, 9. Ignore those. 3, 0, 7 I ignore. 4, 6, ignore my 0. 2, 2, ignore the 7, and a 4. Then I have 0, 0, which I ignore. 1, 1, 8 I ignore. 5, 8 I ignore. 4, 8, 4, 8, 7, 6, 7, 5, and 2. So with this simulation, how many of my repetitions don't have winners? 3 means I won. How many of them don't have winners? Nate's back there going like this. 3. There's no 3 in repetition 1, so I have no winner there. I have 2 winners in that 8-pack. I have no winners here. 2 winners in that 8-pack and no winners there. So for my conclusion, remember, because your simulation will, since we use a table of random digits, this time we would all get the same answer. Up here with the dice, we would have each had different answers. Either way, our conclusion is based on our simulation, so that's how we're going to start our conclusion. So based on this simulation, we would expect an 8-pack. To have no winners. We had 3 8-packs with no winners out of 5. 3 out of 5 is 60%. So we would say 60% of the time. Any questions? Alvin? sorry.
Why did we ignore this number?
So the claim is that 1 in 6 is a winner. So there are 6 possible outcomes. One outcome is I win, and the other 5 are that I lose. So I chose 1 through 6 to work with, and just to make sure that it matched what I did yesterday, I said 3 was a winner, 1, 2, 4, 5, 6 are losers. On the table of random digits, it has 0 through 9, so then I had to specify that I ignored those 4.
Why did you choose 3?
Yesterday, I said, give me a number to represent a win, and Cheyenne was the first one to say 3. You could have chose 1, or 2, or 4, or 5, or 6. Doesn't matter, as long as 1 out of the 6 numbers is a win. Any other questions? All right, so down at the bottom, usually the hardest part of a simulation is coming up with the plan, because you have to make sure that you represent the probability correctly. So the whole 1 in 6 is a winner. So using a dice or using the table of random digits. So the plan part usually is where I see kids get stumped. So we're going to look at a few situations. We're not going to do the whole process or the simulation. We're just going to come up with the plan part. And these are all going to be using the table of random digits. So 1 is picking a random part from a bin containing 20% faulty parts. So what numbers could I use to help me represent that 20% are faulty and 8% work correctly? What does percent make you think of? Zach, what were you going to say?
1 out of 5.
Say that a
1
little.
out of 5.
1 out of 5. 1 out of 5 is 20%. And I actually like that one. I was going to use the fact that percent means per 100 and say you could do 100 numbers. You could have used the numbers 0, 0, 1 to 100. And say that 0, 0, 1 to 0, 20 were faulty. Oops, put my 1 in the wrong spot, sorry. And then 0, 21 to 100 would be working. The only problem with that is that's a lot of numbers to read. I'm abbreviating working. Zach came up with a really nice shortcut. He said 1 through 5 because if we use 1 to mean faulty, that leaves 4 numbers to mean working, and that's 20 and 80%. You could, if you wanted to, also do the numbers 0, 1 through 10. I prefer to read numbers as small as possible. Reading 3-digit numbers you have more opportunity to make mistakes. So I like his. That's the best. I would have to, I almost forgot, specify that 6 through 9 and 0 we would ignore. So you could actually use 100 numbers. You could use 10 numbers. 5 is the smallest amount. You could use 20. As long as 20% of however many numbers you're using is a whole number. I was going to say an equal number, but a whole number. So sometimes you have percents like 23%. 23% of 5 is not a whole number, so we would have to go bigger than that. 23% of 10 numbers is 2.3, so we would still have to go to a larger amount of numbers. So in my opinion, the easiest one here is to do 0, 1 to 100. And you would say 001 to 023 represent those faulty parts, and then 024 through 100 would represent working parts. So sometimes it's easy to use a smaller set of numbers. Sometimes if you have a percent, the easiest way is to just go out of 100. I want you guys to try coming up with the numbers you would use for this one. You have 20% are unfinished, 30% are faulty, and 50% are functioning or working parts. What numbers would you use? And there are multiple answers. So do whatever makes sense for you. There are lots of different ways we can do this. That's the second. Alright, Michelle's going to put one possible answer. If you're on the right track, subtraction doesn't help. I promise. It should be 21. Thank you. So one thing I was noticing walking around, a lot of you chose 10, which is great. Remember for table D, your length, the amount of digits in your label has to be the same. So it has to be 0, 1 to 10. It can't be 1 to 10. When is 1, 1, and if there's a 0 behind it, it suddenly becomes 10. That doesn't make them have the equal chance of being the number chosen. So 0, 1, and 0, 2 are unfinished. 0, 3 to 0, 5 faulty. 0, 6 to 10 would be functioning. The other thing I saw is that some of you would repeat a number in 2 of the categories. So if you use 0, 1, and 0, 2 here, pick up at the next number. Okay? If you went out of 100, which would be absolutely fine, you would have 0, 0, 1 to 20 would be, oops, even I make that mistake, would be unfinished. Then your next set would start at 021. You can't have 020 be unfinished and be faulty. And then you would go through 050 and then 051 through 100 would be the working parts. Yes, sir.
Performing either of those would take like a really long time, right?
It could, yeah. It depends on how many parts they wanted you to pick.
Would it be more efficient to use 0 through 9 then?
You could use 0 through
So
9.
then you're just using one digits?
I would honestly, I was a little surprised Zach didn't do 1 through 5 because 20.
Oh, right.
No, that wouldn't work, would it?
Oh,
No, that's why. But 0 through 9 could work. So you could do 0 through 9, and that would be your 10 numbers, then your reading single digit numbers. Yeah. All right. But a lot of times, even if you're using 3-digit numbers, they'll ask you to do a small set for the simulation. Like just pick 3 parts and tell whether it's faulty, working, or unfinished. Down below are some simulations that have been designed. I want you to read through and figure out if they are valid simulations. So do the percentages match correctly? Really what you're looking at for those.
Okay, so
Right. All right. So a lot of you
I know that.
got on the right track with A, that the cards is what makes it invalid. So this is not valid or invalid, however you want to say it. What is without replacement mean? I shuffle my deck of cards, right? It says shuffle a deck of cards, well, draw one card at a time. Red means they're addicted, black means they're not. So that kid's not addicted. I'm going to keep going until I have 20 cards.
You have to shuffle the deck.
It doesn't say anything about shuffling in between each one. That kid's addicted. Was the probability of getting a red card on the first one the same as the probability of getting a red card on the second one? No. What's the probability of getting a red card on the first one? How many red cards in a deck? 26. How many cards total? 52. So I drew my first card. It was black. What's the probability I get red this time? How many reds are left in the deck? Still 26 of them, right? How many cards are left?
51.
Is that a 50% chance that I get red? No. So cards usually, if it specifies without replacement, are not good because every time you keep a card out, the probability changes. If it says with replacement, meaning I put it back, then it won't be a good design. B, is B valid? Yeah, B is valid. It uses the table of random digits. It specifies which 95% mean the serve is in, which 5% or 5 numbers mean the serve is out. Any questions on those two? We're going to use cards some more. I love cards. How many of you know what's in a deck of cards?
Like the color.
How many colors, how many suits, how many numbers?
Four
suits,
suits.
right?
4 suits.
2 colors.
2 colors. 4 suits. Got that. 4 suits, 2 colors. What else?
2 to 10, ace, 3 2 cards,
2 jokers.
Jokers do not count. If the problem says a standard deck of cards, we don't count jokers. All right, for the sake of saving time, we're not going to do the warm-up from today's packet. No, you're not going to need that right now. All right, so we're going to draw some pictures. Actually, I shouldn't call them pictures. They're diagrams. They're Venn diagrams. How many of these do we need? Just one? 2? 1? Sorry, I thought you were killing me, man. All right, so I'm going to use some Venn diagrams to hopefully help make these ideas make sense. So I think, obviously not an English teacher here, but I think you use Venn diagrams in English.
Yeah.
Okay. I think you use them in history sometimes too, right? Okay. I don't think they put a box around them. In math, we do.
what?
You put a box around your Venn diagram. The box represents the sample space, so it's going to be labeled with S. The sample space holds all the possible outcomes. Okay, so any numbers inside your Venn diagram better add to 1 because your sample space has all the probabilities and all the probabilities add to 1. So complement picture, remember yesterday I taught you the complement rule? The probability that a complement happens comes from 1 minus the probability of A. So my box adds to 1. So if this is A, everything outside the circle but in the box would be A complement. A complement is A not happening. So the circle is the probability A happens. So the probability of A complement would be everything outside the circle but still in the sample space. Mutually exclusive is 2 events that can't happen at the same time. So we're going to have our sample space. We're going to have event A. And we're going to have event B. I will define mutually exclusive down here. So I'm not going to write it up there. Another name for mutually exclusive is disjoint. I try to stick with the wording mutually exclusive, and I'm pretty sure the textbook always uses mutually exclusive, but if you see the word disjoint, like 2 disjoint events, they mean mutually exclusive. So you have A, you have B, they can't happen at the same time, so they're mutually exclusive. Outside of the circle A and the circle B, so everything left in the sample space, would be A complement and B complement. A is not happening and B is not happening. A and B, there is, excuse me, because in math, like I've said before, we're really lazy. So we can't even write the word and a lot. So we use a little, I think of it as an N to help me remember it means and. It really means intersection. So we're looking for the intersection of A and B together. So a lot of times, and this is going to look the most like a Venn diagram. Venn diagrams, you have one circle and another circle, and you have the overlap in the middle, or the intersection. So we're going to say that's event A. This circle is event B. So the intersection, or the overlap of the 2 circles, that's where we would find the probability of A and B. outside the two circles, but still inside that rectangle, would be A complement and B complement. A is not happening and B is not happening. A or B. Again, mathematicians were too lazy to write the word or. That one looks like a U, which is why I've remembered this one that looks like an N means and, because I can't make a U connect to the word or. It just doesn't work for me. N means and, so the other one means or. Really what it means, though, is union, but we use the word or. And or is one of those really misused words in the English language. Like when you go out to eat and you tell them what you want and they go, okay, do you want soup or salad? Can you get both? We'd have to pay extra though, right? When they say soup or salad, they want to know, do you want soup or do you want salad? And you have to pick one. Coffee houses, kinda, because I'm not sure they actually ask this, maybe at restaurants too. You get coffee and they say, do you want cream or sugar? That's the correct use of or, because you can add cream and sugar, both of them, to your cup of coffee. Or means all of it. So if this is A, this is B, here in the middle is A and B. A or B is all of this stuff. Both circles together. Cream or sugar, because I can take both. This says A or, the middle says A and B, yes.
I think I'm just going to use the U, because that makes more sense to me than finding either or.
The U makes more sense to you? I will use the words and the notation interchangeably, because you need to know the notation, but sometimes the word makes more sense for a question, especially if it's like written out in words, a word problem. So I use them interchangeably. I forgot to label this as S, sorry. And outside our two circles is still A complement and B complement. A is not happening and B is not happening. So we will use Venn diagrams, which I will show on this page. Actually, no, I won't. Yeah, that page, sorry. We will use Venn diagrams as one way to create a visual to help us understand the word problem. Another one is two-way tables, which we will look at. And then another one is tree diagrams, which kind of look like when you had to outline your experiments last chapter. Those are the three that I use the most. I'm sure there's other visuals out there, but those are the three that I find most helpful. All right, so like I said, I'm going to define mutually exclusive events. I also put that they're known as disjoint down here. So if you have two events, A and B, they are mutually exclusive or disjoint if they have no outcomes in common. And so can never occur together. So in our picture, that's why the circle with A and the circle with B never touch. They can't happen at the same time. So the probability that A and B happen is 0 because they can't happen together. I'm sorry, say that again. Yeah. That's why I shouldn't talk and write. Sorry. Never occur together. Thank you, Hannah. Never together. Never ever together. That would have made sense, but. Alright, so yesterday, probability rule number 1 was the complement rule. Here's probability rule number 2. It's the addition rule for mutually exclusive events. Lazy, mutually exclusive doesn't get written out much, so if you see ME with periods or without, it means mutually exclusive. So the probability of A or B happening, remember A or B happening is both A and B all together, so we would take the probability of A plus the probability of B. So now we're going to look at an example problem to hopefully put it into a little more context. So, excuse me. Our example problem says that we're going to choose an American adult at random. We're going to define our two events. Event A is the person has a cholesterol level of 240 milligrams per deciliter of blood or above, also known as high cholesterol. Event B, the person has a cholesterol level of 200 to 239 milligrams per deciliter of blood, also known as borderline high cholesterol. According to the American Heart Association, the probability of A, that a randomly chosen American adult has high cholesterol, is 0.16. And the probability of B, that a randomly chosen American adult has borderline high cholesterol, is 0.29. Explain why events A and B are mutually exclusive. Why are A and B mutually exclusive? Say it louder for me. Right, they have no outcomes in common. More specifically, how could we show that? Alex?
To get high cholesterol, you have to have above 240, and then to have borderline, you have to have 239.
Right, there's no overlap. Like Cheyenne said, no outcome in common. But this makes it a little more obvious. So event A is that they have 240 plus milligrams per deciliter, where event B is that they have 200 to 239. You can't have both 240 milligrams per deciliter and 239 at the same time. You either have 240 or you have 239. Question, question 2. Say in plain language what the event A or B is, and then find the probability of A or B. So that just means that we're going to put it into the context of the question. So event A is that they have high cholesterol. Event B is that they have borderline high cholesterol. So event A or B means that the person has high cholesterol or they have borderline high cholesterol. And I'm going to add just a little that it means the randomly chosen American adult. One of these days I'm gonna put some random music into my lessons so I can be like Mr. Weinberg. His songs probably have a point though. Molly's not here. The other day she was in here during 8th period and I said I needed music and she said put on an AP statistics formula song. So I found one. We listened to it. You were here, right, Shelley? No? Somebody else was here. Was it you, Jillian? Maybe it was one of my Algebra 2 kids. It was horrible, but it was a song that had to do with AP statistics. All right, so we put it into plain language. Now, go ahead.
Can we hear this song?
Yeah, let's listen.
Yeah, let's
It was like 10 minutes long,
Maybe
so
our
not
next
today.
Project, our next project should be making a song.
Your next project,
Yeah, to make a song about AP statistics.
No.
No, thanks.
No.
I'll think about it. I have another project, but it's not until like April. But so maybe in between now and then.
Okay.
All right, so then the other part of question 2 is to find the probability of A or B. So we're going to use our probability rule that says for mutually exclusive events, the probability of A or B is the probability of A plus the probability of B, which they told us right here what each probability was. So the probability of A or B is just the probability of A plus the probability of B, which is 0.16 plus 0.29, which would be 0.45. The third question, if C is the event that the person chosen has normal cholesterol, meaning they're below 200 milligrams per deciliter, what is the probability of C? Are you raising your hand, Anna? No. Michelle? Louder.
Oh, 155.
How'd you get that?
Subtract from 100. That would equal 1.
Subtracted from 1. So this, even though it doesn't specifically state it, is a complement rule because we know that disjoint events, anything that's still in our sample space but not in those two circles, they have to add 1. So we know that the probability of event A was 0.16. This was 0.29, and everything has to add to 1. So Michelle just said, okay, what's 1 minus those, which gave her 0.5 with a normal cholesterol. And I think I'm going to stop there because I have about 8 minutes left. So don't lose this packet. We'll finish it on Friday. Don't do the assignment for tonight. If you didn't finish last night's or you struggled with last night's, go back and check the ones you struggled with, see if they make more sense now. And then I'll finish this on Friday and you'll do that assignment over the weekend.
So
Okay?
you're not.
I will sign off on that first one on Friday. Okay? Any questions?